What are the odds? Two stars erupt into sudden naked-eye brilliance. Two powerful earthquakes rip through Venezuelan bedrock, and an interstellar traveler gets battered by a solar storm, all inside a 72-hour window. If you pitched that to a studio, they'd laugh you out of the room. Too implausible, too neatly timed. And yet, here it is. Reality. And reality just staged a performance so synchronized, it feels less like random chance and more like cosmic choreography. Tonight, we're going to dissect this chain of events piece by piece. We'll strip it down with science, nova physics, tectonic stress mechanics, and solar storm modeling. But we'll also venture into the grey territory where coincidence looks an awful lot like pattern. Because what just unfolded in late September 2025 has even the most skeptical minds whispering, what if this isn't random? Part 1. The chain reaction. Two novas lighting up the southern skies, twin earthquakes splitting Venezuelan ground, and a rogue wanderer from another star system colliding with the fury of our sun. All within days, almost as if the universe had marked the same calendar week. It began on September 23rd. Astronomers spotted V1935 Centauri, a nova in the Centaurus constellation. In hours, it leapt to magnitude 5.8, just bright enough for anyone in the southern hemisphere to step outside and catch with the naked eye. Before the astronomical community could even finish digesting that eruption, another star joined the act. V7994 Sagittari, burning into view in the Archer constellation, climbing to magnitude 6.2. Two stellar flares, practically side by side in time, both suddenly visible to anyone watching. Meanwhile, on Earth, nature had its own performance underway. At 22:21 UTC on September 24th, Venezuela shook. A magnitude 6.2 quake struck 24 kilometers east-northeast of Mengrande in Zulia state. The rupture, shallow at just 7.8 kilometers deep, rippled across Venezuela and Colombia. Hours later, at 03:51 UTC, the ground gave way again. This time a 6.3 deeper at 14 kilometers. Twin quakes back to back. Twin novas above, and high overhead, invisible to human eyes but lit up on satellites. The sun was flexing. Forecasters at NOAA's Space Weather Prediction Center tracked a series of coronal mass ejections. Vast clouds of plasma and magnetic field, blasting outward at over 1 million miles per hour. Those eruptions were headed straight into the path of something extraordinary. 3I Atlas, the third confirmed interstellar object ever discovered in our solar system. The symmetry borders on unsettling. Two novas, two quakes, a solar storm colliding with a visitor from deep interstellar space. All within a 3-day window. And the scale, staggering. The novas, light from stars thousands of years distant, arriving this week. The quakes, fractures along the clash zone between the South American and Caribbean plates. The solar storm, an eruption spanning millions of kilometers, racing through the heliosphere. And 3I Atlas, threading its way between Mars and the Sun, its alien ice and dust now tasting the full ferocity of solar cycle 25. No one is claiming a direct causal chain. Earthquakes don't trigger novas. Novas don't steer comets. And yet, the clustering is undeniable. Scientists urge caution. The USGS stresses there's no proven connection between space weather and seismic activity. Solar physicists remind us CMEs are standard fare during solar maximum, and stellar astronomers see novas as natural outbursts of aging binary systems. Still, no textbook prepares you for all of them landing on the same page of history at once. What makes this week truly unique is 3I Atlas, only the third confirmed interstellar visitor, after Oumuamua in 2017 and Borisov in 2019, and the first to encounter a major solar storm near peak solar activity. We've seen what CMEs can do before. In 2007, satellites caught a coronal blast ripping the ion tail clean off comet Encke. Now imagine that same process acting on material forged around another star, surviving millions of years between suns, only to be tested here. The story won't end in September. On October 3rd, 3I Atlas will swing past Mars at just 0.19 AU. Probes in orbit, NASA's MRO, ESA's ExoMars, are preparing to capture what could be humanity's sharpest look yet at an interstellar object. Perihelion comes October 29th at 1:36 AU. Close enough to study, but safe from Earth. Then on December 19th, Atlas makes its closest approach to us, 1.8 AU, closer than Mars at its farthest. Months of opportunity at the exact season when Earth's magnetic field is most vulnerable to solar storms. The data will come, the science will sharpen, but the wonder, the sheer timing remains. Two novas visible from Earth, two earthquakes rattling Venezuela, and an alien traveler colliding with solar fire. Call it coincidence, call it choreography. But either way, September 2025 just rewrote the boundaries of unlikely. Stay with us, because in part 2, we'll dive into those twin novas, the southern sky explosions that announce themselves with photons older than recorded history. But this wasn't just another flicker in the night sky. Within hours of John Seach's discovery report hitting the Central Bureau for Astronomical Telegrams, the big guns in orbit turned their gaze towards Centaurus. And what they saw was extraordinary. NASA's Fermi, gamma-ray space. Telescope flagged bursts of high-energy photons streaming from the nova's direction. Swift, a satellite designed to chase gamma-ray bursts across the sky, swung its X-ray instruments toward V1935, Centauri, and recorded hard X-ray emissions, the unmistakable fingerprint of matter being accelerated to near-light speeds. This wasn't just a pretty glow for backyard observers. It was raw physics at the edge of chaos. Electrons and protons whipped into relativistic motion. Magnetic fields twisted and knotted under unimaginable stress. Shock fronts heating material to tens of millions of degrees. Centauri wasn't simply shining. It was roaring. And then, as if the cosmos wanted to underline the point, a second act followed. Only days later, Seach's watchful eyes caught another eruption, this time in Sagittarius. Sagittarius burst forth, climbing to magnitude 6.2. Two stellar detonations, discovered by the same observer, visible within the same remarkable week. Now, novas themselves aren't rare. Somewhere between 10 and a dozen light up across the Milky Way each year. But for two to brighten near naked-eye visibility within days of each other, that's unusual. The last time astronomers could enjoy such a double act was in 2023, and before that, you'd need to dig years into the archives. So, what are we actually witnessing? Novae are not deaths of stars, but acts of stellar cannibalism. At the heart of each system lies a white dwarf, the dense ember of a long-dead star, crammed with the mass of the Sun into a body no bigger than Earth. Locked in a binary orbit with a living companion, it steals hydrogen from its neighbor, siphoning gas across the void. That stolen hydrogen collects on the dwarf's surface, crushed tighter and hotter under its immense gravity. For decades, centuries, sometimes millennia, the pressure builds, until the tipping point comes. Then, in a single violent flash, the accumulated fuel undergoes runaway thermonuclear fusion. Not the steady fire of a living star, but an uncontrolled detonation. The binary system brightens by factors of 10,000 or more, yet the dwarf itself survives. It simply sheds the ignited layer and begins the slow process again, a cosmic predator forever feeding and flaring. In V1935, Centauri's case, Fermi and Swift showed us just how violent that process can be. Material hurled outward at thousands of kilometers per second. Shock waves strong enough to accelerate particles to relativistic speeds. High-energy radiation erupting across the spectrum. The same physics we find in supernova remnants, in pulsar wind nebulae, even in the hearts of active galaxies. For observers on Earth, both novas favored the southern hemisphere. Centauri sits so far below the celestial equator that northern stargazers could barely glimpse it on their horizon. Sagittarius too hung low for northern observers, but rode high and clear in southern skies, rewarding those under dark skies with a spectacle worth remembering. And just as the stars erupted, so did the scientific community. Seach's reports, channeled through the International Astronomical Union, triggered a global cascade of follow-ups. Telegram Circular 5611 confirmed Centauri. Circular 5612 announced Sagittarius. Within days, telescopes around the world were capturing photometry, measuring the brightness shifts night by night, and spectroscopy, revealing hydrogen, helium, and heavy elements racing outward in the expanding shells. This is where the global network of amateur astronomers proves irreplaceable. Organizations like the American Association of Variable Star Observers mobilize hundreds of dedicated skywatchers who track novas night after night, building light curves that professional telescopes simply don't have the time to record. Their contributions help decode the eruption patterns, plateaus, dips, dust formation episodes, even multi-peaked surges that tell us about the inner workings of these stellar duos. For newcomers, the names can be confusing. V1935 Centauri means it's the 1935th variable star catalogued in that constellation. V7994 Sagittari is the 7th I-994th in Sagittarius. Administrative order doesn't always match discovery sequence, but these permanent labels ensure they take their place in astronomy's growing ledger of cosmic transients. Both stars will fade over the coming weeks and months, but novas are rarely simple. Some cloak themselves in dust after eruption, dimming dramatically before clearing. Others flare again, tracing jagged light curves as their shells expand and cool. Centauri's high-energy emissions already mark it as unusual, and Sagittarius' evolution could yet hold surprises. Mainstream science is firm. These stellar fireworks, occurring thousands of light-years away, pose no threat to Earth. Their light dazzles us, but their energy dissipates across interstellar distances into a whisper by the time it reaches us. No influence, no causal link to solar storms or quakes, and yet the timing is impossible to ignore. 2 novas, 2 Venezuelan earthquakes, a solar storm colliding with an interstellar visitor. Each a separate story, yet written on the same page of September's calendar. Perhaps that's all it is, timing. Or perhaps, once in a while, the universe arranges itself into patterns that feel almost poetic. Because while the stars were exploding light-years away, 7,000 miles from the nearest observatory, the ground beneath Venezuela was preparing its own violent release. Part 3. The Venezuelan Quakes. At 22:21:55 UTC, September 24, 2025, the Earth broke. Beneath Zulia State, just east-northeast of Men Grande, a magnitude 6.2 earthquake ripped through the crust. Its shallow depth, only 7.8 kilometers, meant the rupture's energy blasted upward almost undiluted. Within seconds, the shock rolled across towns, cities, and borders, rattling windows in Maracaibo, swaying buildings in Caracas, and shaking Colombian borderlands. Videos flooded social media, lamps swinging wildly, car alarms wailing, panicked evacuations into the night. But the Earth wasn't done. Barely 5.5 hours later, at 03:51 UTC, a second rupture struck the same zone. This one, magnitude 6.3, deeper at 14 kilometers, but still shallow enough to deliver violent shaking. Its epicenter overlapped the first quake's rupture zone almost exactly. 2 shocks, same region, same day. To understand the significance, you have to remember how magnitude works. The Richter-style scale is logarithmic. A 6.3 releases about twice the energy of a 6.2. Taken together, these twin ruptures released the equivalent of a single quake in the 6.4–6.5 range, enormous by global standards. Aftershocks soon followed. By September 25th, a 5.8 rocked the same fault system, the Earth's way of settling into a new stress balance. Though smaller, it was still powerful enough to inflict damage and fray nerves already tested by back-to-back main shocks. Geologically, the region sits at one of Earth's great pressure points. The South American and Caribbean plates grind and jostle, their locked boundaries quietly storing strain year after year. Fault systems like the Boconó and Oca Ancon Santa Marta crisscross the zone, setting the stage for powerful earthquakes when the accumulated stress finally slips. Depth matters too. The first quake's shallow 7.8 kilometers delivered brutal shaking across the surface. The second, at 14 kilometers, lost some punch but still rattled 2 nations. International seismology agencies logged slight variations in their reported magnitudes, 6.1 to 6.3, depending on methodology, but the conclusion was the same. Venezuela had just endured its strongest seismic episode in years. The human toll went beyond numbers. Evacuations swept through high-rises and hospitals. Emergency teams scrambled to assess bridges, power grids, and critical infrastructure. Early reports suggested surprisingly limited structural collapse, but the inspections continued for days, searching for hidden weaknesses. Historically, the Lake Maracaibo Basin and its surrounding plate boundaries have delivered quakes before, and they will again. Stress transfer between faults means that one rupture can set the stage for another, like dominoes falling underground. And that's why seismologists are watching Venezuela closely in the weeks ahead. But for the millions who felt the ground shift, the question isn't stress transfer or moment magnitude. It's something far simpler. Why now? Why in the very same week that novas erupted above and a solar storm slammed an interstellar visitor? Science says coincidence, yet the story feels anything but ordinary. The earthquakes that struck Venezuela did more than crack walls and sway buildings. They stirred unease across both the scientific community and the general public. Could they be the start of something larger? Statistically, aftershocks are expected. They can rattle the ground for weeks, sometimes months, following a major rupture. The strongest of these typically arrive within days of the main event. Yet beyond that, seismologists remain cautious. The hard truth is that earthquake prediction has never crossed from ambition into certainty. For decades, researchers have searched for precursors, studied fault stress patterns, and developed statistical models. Still, no reliable method exists to forecast if or when another large quake might erupt in the same region. While uncertainty dominated public questions, the global network of seismologists went to work. Every aftershock was logged, every tremor mapped, as monitoring systems captured how stress shifted across fault lines. The Global Centroid Moment Tensor database began its deep analysis, mapping rupture planes, slip directions, and fault orientations, unpacking how the crust had given way beneath Venezuela. Such details allow scientists to reconstruct not just what moved, but how energy redistributed itself across the surrounding region. For people living in Zulia and nearby states, the twin earthquakes carried a blunt reminder of their geological reality. This was a region where the crust itself was restless. In such moments, building codes are tested, emergency plans stretched, and community resilience measured. The damage, while serious, was not catastrophic considering the magnitudes. Part of this was luck. The quakes struck at times when people were largely at home, not in workplaces more vulnerable to collapse. But part was also progress, reflecting improved construction practices and better coordinated emergency response. Still, an unsettling question lingered. Why had such dramatic events clustered in a week already filled with other extraordinary phenomena? 2 novas flaring in the sky, 2 quakes rupturing the ground, an interstellar object threading through the solar system, and above it all, the sun itself bursting with storms. The US Geological Survey has long emphasized a sober view. No physical mechanism has been demonstrated that links solar activity, space weather, or celestial alignments to earthquakes. Time and again, statistical studies attempting to tie sunspot cycles or geomagnetic storms to seismic events have failed to establish solid evidence. Yet the human mind does not let go so easily. When cosmic and terrestrial upheavals arrive together, we instinctively feel there must be a thread connecting them. Perhaps the most responsible scientific stance is to separate the events, study each on its own terms, and resist the temptation to weave premature causal stories. Document the timeline, map the physics, stay open to discovery while guarding against the seduction of coincidence masquerading as connection. And as Venezuela's aftershocks rolled on, the sun was preparing to demonstrate that Earth's immediate neighborhood can be just as volatile as its crust. 93 million miles above the trembling ground, our star was staging its own spectacular eruptions. During those same September days, when novas lit the southern sky and earthquakes broke South America's bedrock, the sun unleashed immense coronal mass ejections, billions of tons of plasma hurled into space, magnetic storms powerful enough to reshape the heliosphere. Coronal mass ejections, or CMEs, begin in the sun's corona, the outer atmosphere where magnetic field lines stretch and twist. When those invisible loops become too tangled, they snap and reconnect with explosive force, releasing energy equivalent to billions of nuclear weapons. Plasma is flung outward at speeds ranging from hundreds to thousands of kilometers per second, capable of crossing the gulf between Earth and Sun in just a few days. NASA's Space Weather Prediction Center models these storms with ENLIL, a sophisticated computer simulation that tracks their paths through the solar wind. The model accounts for density, velocity, and magnetic polarity, forecasting when and where a CME might intersect planets, spacecraft, or anything else in its way. In late September 2025, ENLIL runs revealed a turbulent heliosphere. Multiple CMEs were sweeping through the inner solar system. Against this backdrop, something remarkable unfolded. An intersection of cosmic timelines with no precedent in human history. For the first time, a solar storm was predicted to collide with an object not born of our sun at all, but of another star system. The object was 3I Atlas, discovered only months earlier by the Asteroid Terrestrial Impact Last Alert System. Unlike Oumuamua in 2017 or Borisov in 2019, this interstellar traveler was threading close to the ecliptic plane, right through the busy lanes where solar storms propagate. its retrograde path, moving against the planet's orbital direction, put it on a collision course with one of the sun's outbursts. During solar cycle 25's fiery peak, we already know what can happen when CMEs strike comets. The evidence is not speculative, it has been captured on camera. In 2007, ESA's Stereo spacecraft filmed a CME ripping away the ion tail of Comet Encke, severing it like a thread of smoke. Comets carry two tails, one of dust, pushed gently by sunlight, and one of ions, aligned along solar magnetic field lines. When a CME disrupts those fields, the ion tail can be snapped off entirely, drifting away while a new one begins to form. For 3I Atlas, no spacecraft was stationed nearby to watch directly. The claim that it was struck rests on model-based forecasts rather than eyewitness confirmation. Space weather models excel at predicting general paths, but fine details remain uncertain. If the CME did graze the object, astronomers expected specific signs: a brightened coma, disturbances in the ion tail, or new chemical signatures released as solar plasma bombarded its ancient ices. Amateur astronomers across the world took up the challenge. Coordinated through online networks, they recorded nightly images comparing brightness, tail morphology, and subtle shifts invisible to the naked eye. Their vigilance filled the gaps where major observatories, focused on other targets, might have missed fleeting changes. What unfolds when solar storms strike such a visitor is governed by the same physics that drives flares and geomagnetic disturbances on Earth: magnetic reconnection. It is an elegant but violent process, field lines linking, breaking, and relinking, converting stored magnetic energy into the motion of charged particles. In this case, it was not Earth, but a fragment of another star system that bore the brunt. I Atlas, only the third confirmed interstellar object in history, carried within it material formed around an alien sun shaped billions of years ago. To see it subjected to our own star's fury was more than spectacle. It was the first recorded moment our sun directly interacted with matter from beyond its stellar family. And this time, unlike with Oumuamua or Borisov, the geometry made such interactions far more likely. Atlas lingered longer near the ecliptic, exposed to the storms that concentrate along the solar system's equatorial plane. Solar cycle 25 had reached its peak, making the environment especially hostile. Frequent flares, dense sunspots, and CMEs flung outward like artillery. The timing was exquisite, if unforgiving. Whether the CME altered Atlas's behavior remained an open question. Analysis of brightness shifts, spectroscopic data, and tail morphology would continue for weeks. But already, the larger implications loomed. If we could document how our star reshaped an interstellar object, we might glimpse how stars across the galaxy interact with debris passing through their domains. Atlas itself may carry scars of past encounters, each star system leaving an imprint as it wandered through interstellar space for millions of years. As September closed, the world found itself staring at an improbable timeline: novas, earthquakes, solar storms, and the first interstellar traveler caught in direct confrontation with our star. Were these events connected or simply crowded into the same calendar week by chance? Science urged caution, but human imagination tugged in another direction. The question would hang unresolved as Atlas continued its journey toward a close pass by Mars in early October, perhaps carrying with it the subtle fingerprints of a solar storm from our restless star. Part 5. Weirdness framed now. Step back. Look at the canvas we've assembled. 2 novas blazing in the night sky, 2 earthquakes rupturing the Earth within hours of one another, solar storms sweeping across interplanetary space, an interstellar visitor drifting through the inner solar system at the very moment of peak solar fury. It was as though the universe had condensed a decade's worth of drama into a single week. Too much, too fast, and it forced a collision between 2 very different modes of thought: the discipline of science and the instinct of human pattern-seeking. Evolution shaped our brains to connect dots. A rustle in the grass might mean a predator, a gathering of clouds might signal rain, social gestures hint at danger or opportunity. To see patterns is survival, but the same architecture that once protected us can also mislead, making coincidence feel like fate. The scientific consensus is blunt. The US Geological Survey has not found and does not endorse any causal link between solar storms and earthquakes. Statistical tests across decades have failed to reveal predictive power. Seismologists emphasize that, even today, earthquakes cannot be reliably predicted from any precursor, terrestrial or cosmic. Stellar astronomers, for their part, remind us that novas are not mysterious omens but well-understood thermonuclear runaways on white dwarfs, the predictable outcome of binary star evolution, and yet, clustered together, the events feel heavy with significance. Human culture has always searched for meaning in the skies. From comets once feared as harbingers, to eclipses interpreted as cosmic judgment, the end of September 2025 carried that same aura, pressing the question, were these events merely neighbors in time or participants in some larger unseen order? Science tells us to separate them, to analyze each phenomenon on its own terms. But culture, memory, and imagination will always bind them together in story. That too is part of the human experience. As September's extraordinary week ended, what remained was both a dataset and a narrative. Numbers and light curves for the scientists, awe and wonder for the public. A reminder that the cosmos often delivers its drama in clusters, daring us to decide whether the meaning lies in mechanism or in the patterns we cannot help but see. The rhythm of nova eruptions is set by stellar physics, not by the movements of planets, earthquakes, or the moods of the solar wind, V1935 Centauri and V7994. Sagittari are not omens. They are ordinary, if spectacular, products of galactic processes playing out across thousands of systems. Solar eruptions, too, follow their own cycles. Coronal mass ejections erupt when tangled magnetic fields in the Sun's outer atmosphere snap and release energy, a pattern that intensifies during solar maximum. In that sense, late 2025 was always destined to be a busy season for space weather. Likewise, the interaction between solar storms and cometary gas has been observed and modeled for decades, a matter of plasma physics rather than cosmic mystery, and yet, acknowledging this science doesn't erase the strangeness of timing. Sometimes, unrelated events stack together so neatly that coincidence begins to resemble choreography. The question becomes, how do we stay faithful to skepticism without discarding the sense of awe such alignments inspire? Our framework here is simple. At the base lies raw observation, brightness measurements, spectra, quake records, satellite detections. From that base, we ascend into interpretation grounded in physics and established models. Above that, carefully marked, lies speculation, the space where imagination tests unproven ideas, from solar activity influencing Earth's crust to possible cosmic terrestrial linkages. Each level has its place, provided the boundaries stay clear. To carry a general audience through this journey, some definitions matter. A nova is a runaway thermonuclear outburst on a white dwarf, caused when its companion star feeds it hydrogen until ignition. It differs fundamentally from a supernova, which destroys the star itself. A coronal mass ejection is a cloud of charged plasma hurled from the Sun at hundreds to thousands of kilometers per second. Perihelion is simply the closest point in an orbit to the Sun. An astronomical unit, about 150 million kilometers, is the scale we use to measure those orbits. Comets grow glowing ion tails when solar wind strips electrons from gases in their coma. Those ions then trace magnetic field lines straight away from the Sun, creating luminous streamers millions of kilometers long. That groundwork matters, because what comes next will separate fact from conjecture. We'll examine the physics of novas, earthquakes, and solar storms on their own terms, while tracking 3I Atlas through its October Mars flyby and perihelion passage later that month. We'll weigh standard science against adventurous hypotheses, without blurring them. September's solar storms also arrived under the influence of the Russell-McLaren effect, a seasonal tilt in Earth's magnetic field that makes September and October especially fertile for geomagnetic disturbances. That context alone explains why late September often brings heightened auroral and space weather activity, regardless of novas or earthquakes. Still, 3I Atlas is no ordinary comet. It is only the third confirmed interstellar visitor, and uniquely, the first to be observed amid an active solar maximum. Its trajectory along the ecliptic plane ensures a front-row encounter with space weather and maximizes opportunities for coordinated spacecraft and telescope campaigns. Unlike Oumuamua, which departed too quickly for close study, or Borisov, which never came near enough, Atlas will linger in view for months. This gives Mars orbiters like ESA's ExoMars and NASA's Mars Reconnaissance Orbiter a rare chance to image an interstellar nucleus as it brushes past the red planet on October 3rd. Ground observatories will continue monitoring its brightness, chemistry and morphology through late autumn, capturing in real time how alien ices respond to solar storms. Meanwhile, seismologists in Venezuela continue to monitor the aftershock sequence from September's twin quakes. Major earthquakes are often followed by weeks or months of smaller tremors, but predicting whether a larger rupture will follow is beyond present science. The region sits atop a notoriously complex plate boundary where the South American and Caribbean plates grind together, a zone where earthquakes are guaranteed, but not forecastable. Through all of this, our promise is transparency. Mainstream explanations come first because they rest on decades of physics and observation. Speculative links can be explored, but never smuggled in as fact. And above it all sits the human need to make sense of patterns. It's worth remembering that we live in the first era of history capable of seeing these connections at all, of spotting interstellar travelers, monitoring seismicity worldwide, watching novas flare across the galaxy, and tracking solar storms in near real time. Earlier generations might have noticed the stars brighten and felt the Earth shake, but they could not have placed those experiences in a cosmic frame. So, how does a star erupt without obliterating itself? That takes us into the anatomy of a nova. Imagine a white dwarf, a stellar core collapsed to the size of Earth, but containing the mass of our Sun. Matter here is crushed to densities 1,000,000 times greater than water. Temperatures soar to tens of thousands of degrees. Now imagine this stellar ember orbiting a swollen red giant. The dwarf's gravity pulls hydrogen from its companion in a steady siphon. That gas accumulates on the white dwarf's surface, compressed under unimaginable gravity. For decades or centuries, nothing happens, until the critical temperature of about 100 million Kelvin is reached. Then, in seconds, runaway fusion ignites. The eruption releases as much energy as our Sun produces over thousands of years. But the white dwarf itself survives, shedding only its stolen hydrogen in a violent flash before starting the cycle anew. That is why September's novas caught the attention of satellites. NASA's Fermi telescope detected gamma rays from particles accelerated to near light speed. SWIFT recorded high-energy X-rays from spiraling electrons. These eruptions are not just pretty stars. They are natural particle accelerators, shock waves racing outward at thousands of kilometers per second, energizing matter the way Earth's most advanced laboratories dream of doing. Amateurs play a critical role in this science. Organizations like the American Association of Variable Star Observers collect thousands of brightness estimates from observers across the globe. These provide continuous monitoring that large observatories, spread thin across many targets, cannot achieve alone. Patterns emerge. Novas rise to naked eye visibility in days to weeks, linger for days or months at peak, then fade slowly, sometimes with afterglows and secondary flares. Spectra reveal the chemistry of the ejected gas, its velocities, its cooling phases, and its eventual transformation into a faint shell expanding across interstellar space. Both V1935 Centauri and V79994 Sagittari lie thousands of light years away. Their light left long before humans built cities or wrote language. Only now, in September 2025, did those photons finally arrive to meet our detectors and our eyes. Just as quakes rattled Venezuela and solar storms brushed an interstellar traveler. Coincidence? Almost certainly, but remarkable nonetheless. Even with modest tools, amateurs can join this watch. A DSLR with a telephoto lens can capture the nova's fading glow. Binoculars and backyard telescopes can estimate their magnitudes. More advanced setups with CCD cameras and filters can chart light curves that add scientific value. In this sense, the story of September 2025 is not only about cosmic processes, but also about human participation in the act of noticing. Astronomical naming conventions may appear cryptic, but they reflect a deep tradition. Take V1935 Centauri. The V denotes a variable star, and the number marks it as the 1935th variable formerly catalogued in the constellation Centaurus. This permanent designation replaces the temporary discovery labels that often carry a discoverer's name, survey catalogue number, or date stamp. Such designations anchor novas in the long-standing record of stellar variability, a practice that links modern astronomy to centuries of systematic sky-watching. Among the most fascinating features of nova evolution is dust creation. In the weeks or months following an eruption, certain novas undergo dramatic fades in brightness. This occurs when the ejected gas cools enough for microscopic dust grains to condense. These newly minted particles scatter and absorb light, producing dust dips that can dim a nova by several magnitudes. Eventually, the dust is either blown apart by the nova's continuing radiation or dispersed into interstellar space, allowing the central star to shine through again. The scale of energy release remains staggering to human imagination. A typical nova radiates as much energy as our sun produces over 10,000 years, power sufficient to fuel our civilization billions of times over. Yet in the hierarchy of stellar explosions, this output is modest. Supernovas dwarf novas, unleashing so much light that they can outshine entire galaxies. Some white dwarfs, however, are not one-time performers. Recurrent novas erupt every few decades, cycling through dozens of explosions over astronomical timescales. With each outburst, the white dwarf gains mass from its companion, inching toward the Chandrasekhar limit, where the star itself could ultimately detonate as a Type Ia supernova. Observations of September's novas continue across the electromagnetic spectrum. Ground-based telescopes record optical brightness and shifting spectra, while space-based instruments, like the Hubble Space Telescope, may resolve expanding shells of ejected material. Radio arrays detect synchrotron emission from high-speed particles accelerated in the nova's blast. The classification of V1935 Centauri and V79994 Sagittari as classical novas rests on these multi-wavelength datasets. Their light curves and spectral fingerprints match those expected from thermonuclear runaways, distinct from the smaller flares of dwarf novas or the peculiar colors and timelines of luminous red novas, likely caused by stellar mergers. Still, astronomy thrives on skepticism. Could either of these be something more exotic? Current evidence favors the standard nova model, but the discovery of gamma-ray emission from V1935 Centauri hints at deeper physics. Gamma-ray novas belong to a relatively new class of stellar phenomena. Their high-energy emissions reveal surprisingly efficient particle acceleration, possibly through magnetic reconnection or powerful shock fronts in the ejected gas. Such processes blur the line between nova physics and the mechanisms behind supernova remnants and cosmic rays, suggesting novas may play a larger role in the galaxy's high-energy ecosystem than once believed. While these stellar fireworks unfolded across light-years of distance, Earth's crust reminded us that it too is capable of sudden, violent release. Part 7. Anatomy of a Quake. Clustered beneath Lake Maracaibo and across Venezuela's Zulia state lies one of South America's most tectonically tangled regions. Here, the Caribbean plate collides and slides against the South American plate, producing a mosaic of faults. The Bocono system cutting northeast-southwest through the Andes, the Oca-Ancon fault running east-west along the Caribbean coast, and the Santa Marta fault stretching into Colombia. These fractures accumulate stress over decades, stockpiling energy until the crust yields in sudden jolts. At 22:21 UTC on September 24th, a magnitude 6.2 earthquake ruptured roughly 7.8 kilometers below the surface. At such shallow depth, the seismic waves had little time to attenuate, delivering strong shaking across western Venezuela and into Colombia. The rupture extended for several kilometers, displacing rock by meters in a matter of seconds. Compressional P waves reached seismographs first, followed by side-to-side S waves and slower-moving surface waves that rolled the ground in swells, felt for minutes. Barely 5.5 hours later, at 03:51 UTC on September 25th, a second rupture struck. This time, the magnitude 6.3 quake originated deeper, around 14 kilometers, but still shallow enough to produce destructive shaking. The near back-to-back timing reflects a principle of stress transfer. When one fault segment ruptures, it redistributes stress to neighboring faults. Some zones are relieved, while others are pushed closer to breaking. The first quake likely primed the adjacent segment that failed in the second. Though the magnitude difference between 6.2 and 6.3 may seem minor, the logarithmic scale means the second released nearly twice the energy of the first. Together, the pair equaled a single event of about magnitude 6.4 to 6.5, one of the most powerful seismic releases worldwide that week. Seismological agencies reported slightly different magnitudes, a normal outcome of using varied measurement methods. The USGS calculates moment magnitude derived from total energy release, while European centres often rely on wave amplitude or frequency analyses. As more stations report in, magnitudes are refined, explaining why news outlets reported ranges for the first quake. The aftershocks came as expected. Later on September 25th, a magnitude 5.8 tremor struck, strong enough to be felt widely, though smaller than the main shocks. Omori's law, formulated over a century ago, predicts that aftershock frequency decays with time. The largest aftershocks usually occur within days, with smaller ones trailing for weeks to years. On the ground, residents evacuated high-rises as buildings swayed, light fixtures rocked and windows rattled. Videos on social media captured the surreal mix of fear and resilience. Though major structural damage was limited, assessments focused on hidden vulnerabilities in older construction. Venezuela's tectonic setting ensures this won't be the last such test. The same faults responsible for these quakes have generated magnitude 7 events in the past, and they will again, though science cannot yet say when. Speculation sometimes surfaces. Could solar storms or other cosmic events trigger quakes? The scientific consensus remains firm. No reliable correlation exists. Solar flares, CMEs, or geomagnetic storms produce forces far too weak compared to the stresses driving tectonic rupture. Minor influences, like atmospheric pressure or tidal forces from the moon, are measurable but trivial against the locked energy of a fault on the verge of failure. Seismologists instead rely on statistical forecasts. After a large quake, the odds of another in the region rise temporarily due to stress transfer. But the forecasts speak in probabilities, not dates. Preparedness, through building codes and emergency systems, remains humanity's most effective defense. Part 8. The Sun at Maximum. While Earth shook, the Sun too was in rare form. Solar Cycle 25 reached its peak in 2024-2025, a time when our star sheds its calm facade and reveals its turbulent heart. On September 24th and 25th, as novas brightened and Venezuela rattled, the Sun's own fury surged. One key index of solar activity, the 10.7 centimeter radioflux, hovered between 180 and 190 solar flux units, well above the 150 threshold for heightened activity and near the 200 mark that signals conditions ripe for major storms. Each reading reflects the number and strength of active regions on the Sun's face. Sunspots, some wider than Earth, darkened the photosphere. These marks are the footprints of tangled magnetic fields punching through the surface. In their cores, field strengths exceeded 3,000 Gauss, thousands of times stronger than Earth's own magnetic field. The more sunspots, the more opportunities for those magnetic lines to twist, reconnect, and unleash explosive flares or coronal mass ejections. During solar maximum, the Sun's global magnetic field ceases to behave like a neat dipole. Instead, it becomes a snarl of knots and loops, with active regions persisting for weeks as they rotate across the solar disk. CMEs arise when this magnetic tension becomes too great, releasing billion-ton plasma clouds at hundreds to thousands of kilometers per second. NOAA's Space Weather Prediction Center tracks these storms using the WSA-Enlil model, which simulates how CMEs propagate through the heliosphere. Though powerful, the model cannot predict every detail, since CMEs vary in shape and structure. Still, it can provide broad estimates of when a storm might arrive at Earth, Mars, or interstellar visitors like 3I Atlas. Adding to the drama, September fell near the autumn equinox, when the Russell-McFerrin effect comes into play. This seasonal alignment of Earth's magnetic field with the solar wind amplifies geomagnetic coupling, often making equinox storms the year's most intense. This geometric alignment stems from the way Earth's magnetic field tilts relative to the interplanetary magnetic field carried outward by the solar wind. Around the equinoxes, this geometry favors magnetic reconnection between solar wind lines and Earth's magnetosphere, setting the stage for stronger geomagnetic disturbances. Even moderate solar eruptions can therefore trigger powerful storms, with effects reaching far beyond the colorful auroral displays that capture public imagination. Geomagnetic storms disrupt high-frequency radio used by aviation and maritime industries, force satellite controllers to counter increased atmospheric drag, and in severe cases threaten electrical grids through geomagnetically induced currents. To help industries prepare, NOAA maintains standardized indices: the G scale for geomagnetic storms, the S scale for solar radiation storms, and the R scale for radio blackouts. The Sun's impact extends even to comets, which serve as natural laboratories for plasma physics. As solar wind streams past a comet, it strips electrons from gases in the coma, creating charged particles that form long ion tails aligned with magnetic field lines. These glowing filaments, stretching millions of kilometers, provide visible evidence of otherwise invisible processes. When a coronal mass ejection collides with a comet, the results can be spectacular. In 2007, ESA's STEREO spacecraft watched as a CME tore away the ion tail of comet Encke, leaving it to drift off into space while a new tail reformed. A vivid demonstration of magnetic reconnection at work. Against this backdrop of heightened solar activity, interstellar object 3I Atlas began its approach. Unlike earlier visitors that passed through quieter cycles, this traveler entered the inner solar system during peak solar turbulence. Its trajectory along the ecliptic plane exposed it to frequent CMEs, maximizing the chance of dramatic interactions. The physics of CME propagation involves tangled magnetohydrodynamic processes spanning scales from individual particle gyrations to structures larger than planets. Fast CMEs plow into slower solar wind, forming shock fronts that accelerate particles to extreme energies. Sometimes multiple CMEs interact, merging into vast disturbances or creating magnetic knots that intensify reconnection and particle acceleration. To track these events, forecasters draw on a global suite of instruments. NASA's Solar Dynamics Observatory provides continuous high-resolution imaging of the solar surface. SOHO monitors eruptions from the Sun's far side. The ACE spacecraft, stationed between Earth and the Sun, offers advance warning of incoming plasma streams. Even amateur radio operators contribute real-time reports of ionospheric changes that alter signal propagation during storms, sometimes enhancing long-distance contacts, sometimes erasing them entirely. Cycle 25 appears to be following a double-peaked pattern, with intense activity in 2024 continuing into late 2025. This extended maximum means the risk of severe space weather may persist into 2026, keeping Earth and its technologies under constant pressure. Meanwhile, aurora photography has surged in popularity, with social media filled with dazzling greens, reds, and purples swirling across the skies. These lights trace the invisible link between solar eruptions and Earth's upper atmosphere, where incoming particles excite oxygen and nitrogen atoms that glow as they release energy. The solar wind itself carries embedded magnetic fields, stretched outward across the heliosphere, a vast electromagnetic web that connects planets, comets, and spacecraft all the way to the heliopause, the frontier where solar influence yields to the interstellar medium some 100 astronomical units away. In September 2025, as forecasters mapped solar storms racing through the heliosphere, one target captured particular attention: the interstellar traveler 3I Atlas, threading its way toward a historic first encounter with another world. Part 9. 3I Atlas on approach on July 1, 2025. The Asteroid Terrestrial Impact Last Alert System detected a faint object shifting against the background stars. At first, it resembled a distant comet, but orbital calculations quickly revealed something far more significant: the third, confirmed interstellar visitor in human history, following Oumuamua in 2017 and Comet Borisov in 2019. Its designation, 3I Atlas, tells the story. The 3I for Third Interstellar, and Atlas in honor of the telescope array that first spotted it. This visitor arrived under uniquely favorable circumstances. Unlike its predecessors, it was bright enough for extended study, moving in the ecliptic plane where most solar system activity occurs, and entering during solar maximum, conditions that would highlight how our star influences alien material. Its hyperbolic orbit, with eccentricity well above 1, proved its foreign origin. Traveling on a retrograde inclination of nearly 175 degrees, it cuts against the normal planetary flow. Estimates of its size remain uncertain, anywhere from a few hundred meters to perhaps 15 kilometers. At such distances, even powerful telescopes cannot resolve details. The object appears only as a diffuse point of light surrounded by a faint coma. Brightness models depend on assumptions about reflectivity and activity level, both unknown for something born around another star. A pivotal opportunity looms on October 3, 2025, when 3I Atlas will pass within 0.19 AU of Mars, just 28 to 30 million kilometers away. From orbit, spacecraft such as ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter will enjoy an extraordinary vantage point. MRO's high-rise camera, though unable to resolve fine surface detail, may detect coma structure and condensation, while spectrographs could reveal the composition of escaping gases: cyanogen, carbon monoxide, carbon dioxide. These molecules would provide rare clues about the chemistry of a world forged in another stellar nursery. Amateur astronomers have joined the effort, contributing light curves and morphology sketches as the comet brightens. The southern hemisphere has the best view, though northern observers can glimpse it in early morning skies. Coordinated campaigns through organizations like the AAVSO and Minor Planet Center ensure continuous monitoring. After the Mars flyby, the object will swing inward to perihelion on October 29th at about 1:36 AU. It will come closest to Earth on December 19th, passing at 1.8 AU, 270 million kilometers, still closer than Mars at its farthest. Observers with modest telescopes will continue to track its evolution into early 2026. Scientists will watch to see whether it behaves like an ordinary comet or displays unusual features betraying its interstellar origin. Solar heating could unleash volatile compounds frozen since its ejection from its birth system, producing sudden brightness surges, tail formation, or other unexpected phenomena. Already, images suggest dust tails and ion tails forming in familiar but subtly different patterns, hinting at the complex physics at work. Its true size and activity remain uncertain, awaiting infrared measurements and refined models. Media reports of a 15-kilometer body remain speculative. What is certain is that 3I Atlas arrives at a time when Earth's skies promise not just one spectacle, but two. Part 10. Comet Swan joins the stage while 3I Atlas captures headlines. October 2025 brings another visitor that could steal the show. Comet C2025R2, Swan. Discovered in SOHO Swan data by amateur astronomer Vladimir Bezugly on September 11-12th, this long-period comet is making its first recorded dive into the inner solar system. Bezugly spotted it while combing through public hydrogen maps from SOHO's Solar Wind Anisotropies instrument. The object brightened rapidly as it approached perihelion on September 12th, confirming its cometary nature. Its orbit favors excellent October visibility, especially as it nears Earth on October 20th-21st. If predictions hold, Comet Swan could brighten to magnitude 4.6, potentially visible to the naked eye under dark skies and easily seen through binoculars. Its behavior, however, is uncertain. First-time comets can brighten unpredictably or fade without warning. For skywatchers, the coincidence is extraordinary. In the same weeks that 3I Atlas brushes past Mars, Comet Swan will sweep past Earth, offering naked-eye views for millions. Together, these cosmic travelers ensure that October 2025 will be remembered as one of the great months of modern skywatching. The new moon of October 20th and 21st removes one of the greatest obstacles to comet watching, moonlight, that often drowns out faint celestial objects. The timing could not be better. The Orionid meteor shower, born from debris shed by Halley's Comet, reaches its annual peak on the very same nights. Under clear dark skies, observers may witness a rare convergence, an interstellar visitor evolving before our eyes. A bright long-period comet sweeping past Earth, and dozens of meteors flashing overhead each hour. For skywatchers, it is a moment of almost theatrical design. Yet beneath the spectacle lies deep scientific contrast. Comet Swan, a long-period visitor from the outer reaches of our own solar system, is a child of familiar origins. It likely formed 4 billion years ago in the cold outskirts of the protoplanetary disk, spending most of its existence frozen in the distant Oort cloud until a gravitational nudge sent it sunward. 3I Atlas, by contrast, was born around another star, its chemistry and structure shaped in an entirely foreign stellar nursery. While both comets carry familiar ingredients, water ice, carbon monoxide, carbon dioxide, organic molecules, their formation environments differ profoundly. The questions they pose mirror these differences. 3I Atlas offers a glimpse into how planetary systems beyond our own assemble, and how cosmic radiation alters matter during million-year journeys between stars. Swan, on the other hand, tells us about the early history of our own solar system, what materials filled the Oort cloud, and how pristine ices respond to solar heating on a first passage into the inner system. October's double comet display also brings extraordinary photographic opportunities. Wide-field cameras can capture both objects in a single frame, documenting their relative positions, tail structures, and changing brightness. Time-lapse sequences could reveal night-to-night shifts in coma shape, tail orientation, and luminosity. Solar-wind interactions add another layer of unpredictability. Coronal mass ejections can sever ion tails in dramatic disconnection events, sometimes visible even through amateur telescopes. Predicting comet behavior remains notoriously difficult. Some comets flare spectacularly, developing immense tails and becoming unmistakable naked-eye objects even over city lights. Others fade, fragment, or fail to meet expectations. For Comet Swan, with no observational history to guide predictions, uncertainty is particularly high. Unlike periodic comets that reveal their tendencies over repeated returns, first-time visitors offer no precedent. Outgassing rates, structural integrity, and brightness evolution remain unknowns. Amateur astronomers play a vital role in reducing this uncertainty. By estimating brightness through comparisons with nearby stars, and by capturing digital images that record coma and tail changes, they provide continuous data that large observatories cannot. Professionals, meanwhile, employ spectrographs to detect emissions from CN, C2, oxygen, and NH2, each line revealing which volatiles are evaporating from the nucleus under solar heating. Side by side, these studies will allow scientists to compare the chemistry of an interstellar wanderer with that of a long-period solar system comet. For observers on the ground, success will depend on preparation. Rural or wilderness skies will be essential, since urban light pollution erases much of the spectacle. Weather in late October varies widely, requiring flexibility. Binoculars, often better than telescopes for comets, provide a wide enough field to capture the nucleus, coma, and tail in full context. Models like 7SAMI50 or 10X50 strike the balance between light-gathering power and comfortable viewing. The safety risks are virtually non-existent. Unlike solar eclipses, comets require no filters or precautions beyond dressing warmly on chilly October nights. Instead, the main challenges are logistical: finding dark skies, dodging clouds, and keeping equipment functional in the cold. Educational opportunities multiply when such phenomena align. Astronomy clubs, schools, and public observatories are already planning viewing nights, using the occasion to introduce newcomers to comet science, while offering seasoned observers a rare chance to compare two bodies of fundamentally different origin. Public events of this kind nurture not only scientific literacy, but also a sense of shared wonder, reminding people that the universe still writes stories visible to the naked eye. As October 2025 unfolds, the skies will stage an extraordinary sequence: an interstellar visitor passing Mars, a long-period comet sweeping near Earth, heightened solar activity shaping their evolution, and meteor showers painting the atmosphere with streaks of light. These convergences span every scale of natural process, from the shifting crust of our planet, to the chemistry of frozen ices, to the violent cycles of stars. To make sense of such a clustering, we turn to patterns. Human minds are built to connect events, to weave separate occurrences into narrative, and the timeline of late September and October 2025 invites exactly that. September 23rd, Nova V1935. Centauri erupts into naked-eye visibility in Centaurus. September 24th, a magnitude 6.2 earthquake strikes Venezuela at 22:21 UTC. September 25th, Nova V794 Sagittari explodes in Sagittarius. Hours later, a magnitude 6.3 quake ruptures the same Venezuelan region, followed by a 5.8 aftershock. Late September, models predict coronal mass ejections crossing the path of 3I Atlas, October 3rd. The interstellar visitor brushes past Mars at 0.19 AU October 20th, 21st. Comet Swan makes its closest pass to Earth, just as the Orionids peak under a new moon. October 29th. 3I Atlas reaches perihelion at 1:36. AU 2 novas in 2 nights. 2 major quakes in 2 days. solar storms threading through interplanetary space, an interstellar visitor near Mars, a naked-eye comet near Earth, a meteor shower igniting at the same time. The compression of such events feels less like chance and more like choreography. Yet the scientific mainstream counsels restraint. The US Geological Survey finds no credible evidence linking solar storms to earthquakes. Seismologists confirm that aftershocks and stress transfer explain the Venezuelan events. Astronomers describe novas as natural outcomes of binary star evolution. Solar physicists attribute coronal mass ejections to magnetic processes inherent to solar maximum. Each phenomenon has a clear, independent explanation, and still, the clustering feels uncanny. Human brains are wired for pattern recognition, a survival mechanism that now leads us to perceive significance even in coincidences. Psychologists call it apophenia, the tendency to see connections in random events. The challenge, then, is balance. We must hold rigorous skepticism alongside genuine wonder. We can recognize the independence of these processes, while also acknowledging the beauty of their timing. Science explains each event. Poetry arises from their convergence. History shows we are not the first to wrestle with this duality. Ancient cultures read comets as omens, eclipses as warnings, earthquakes as divine messages. Today, we know more about the mechanisms, but the urge to find meaning in cosmic synchronicity persists. The late 2025 cluster reminds us of both truths, that natural law governs the universe, and that human perception is drawn to patterns. The former grounds us in reason, the latter lifts us into awe. And perhaps it is in holding both together, skepticism and wonder, that we best honor moments like these. These archetypal associations carry a unique power. They echo through deep psychological patterns and offer storytellers rich symbolic material, even when detached from physical causation. The challenge, and the invitation, is to hold multiple perspectives at once. To respect scientific rigor, while also appreciating the wonder that arises when cosmic events cluster in synchronistic ways. We can lean into speculation without abandoning skepticism, celebrate the extraordinary without ignoring the probable. Perhaps the most honest stance is one of balance, to embrace uncertainty while remaining open to discovery. Science does not advance by premature certainty, but by careful observation, the crafting of hypotheses, and rigorous testing. The convergence of events across September and October provides fertile ground, not only for scientific inquiry, but also for human imagination, so long as we distinguish clearly between what is observed, what is hypothesized, and what is actually known. As we venture further into these questions, one controversial line of speculation stands out: the possibility that space weather might, in some subtle way, influence seismic activity on Earth. Part 12. Space weather and earthquakes, the Yaids. Suggestion that solar storms could play a role in triggering earthquakes remains one of the most persistent and disputed hypotheses in Earth-space science. For decades, researchers have reported statistical correlations between geomagnetic disturbances and seismic activity. Yet a clear, physically plausible mechanism that could link solar events 93 million miles away to sudden ruptures in Earth's crust has never been firmly established. One of the more intriguing recent ideas comes from researcher Stephen Burns. He proposed that when high-speed solar wind streams abruptly thin out, leaving behind a region of much lower density, the resulting drop in electromagnetic pressure could disturb Earth's magnetosphere. These shifts, in turn, might propagate through the ionosphere and into the crust, potentially altering stress conditions in rocks. The chain of effects, magnetospheric changes, ionospheric currents, induced electromagnetic fields, and finally piezoelectric responses in crystalline rock, does exist in theory, but the magnitudes are exceedingly small. Nanotesla-scale magnetic fluctuations and microstrain stress changes, thousands of times too weak to trigger quakes in faults not already on the brink of rupture. What has been firmly documented is less a mechanism than a literature of correlations. Since the mid-20th century, studies have reported apparent associations between solar flare frequency and earthquake timing, or between geomagnetic storm strength and seismic clustering. Many of these initial reports claim statistical significance, but attempts at replication often failed when applied to other regions, different time periods, or broader earthquake catalogues. Publication bias complicates the picture. Studies finding positive correlations are more likely to be published and cited, while those reporting null results are quietly shelved. As a result, the research landscape can give a misleading impression of consensus. Meta-analyses that combine data across multiple studies usually show that any effect shrinks as sample sizes grow and methodologies become more rigorous. The United States Geological Survey, along with leading international seismological organizations, has consistently reaffirmed the same conclusion. No reliable evidence supports a causal link between solar storms and earthquakes. Comprehensive analyses comparing global earthquake records against solar activity indices across multiple decades and solar cycles have failed to reveal consistent patterns once statistical biases are corrected. Still, some researchers continue to probe niche possibilities. Geomagnetic storms, for example, can generate induced electric currents in conductive materials underground, such as aquifers or mineral deposits. In theory, these could influence pore pressure or rock chemistry within fault zones. Atmospheric pressure changes associated with geomagnetic storms have also been considered, though their scale, typically less than 1 millibar, is far too small compared with normal weather fluctuations that show no clear seismic effects. The only external forces that have been conclusively shown to modulate earthquake timing are gravitational, earth tides caused by the moon and sun. These effects are measurable, well understood, and can slightly elevate the probability of quakes when tidal stresses align with fault orientations already near failure. But even here, the influence is subtle, shifting timing rather than creating quakes outright. By comparison, planetary alignments, popular in speculative theories, exert gravitational effects so weak that they are dwarfed by ordinary lunar tides. Testing whether space weather has any measurable role in seismic activity is further complicated by the statistical noise of earthquakes themselves. Seismicity is inherently clustered in space and time, and aftershock sequences can mimic external correlations. Space weather indices also display cycles and clustering, making coincidental overlap inevitable. The only way to move forward scientifically is with pre-registered studies, blind testing, and clearly defined hypotheses applied prospectively to fresh datasets. Such rigor remains rare in this field. To constitute compelling evidence, three things would be needed: a physically plausible mechanism, modeled or demonstrated in laboratory conditions; a statistical signal that holds predictive power across independent datasets; conditional results tied to specific tectonic settings or stress conditions, rather than universal effects. The Venezuelan quakes of late September occurred amid heightened solar activity, adding one more data point to an already controversial debate. But as seismologists emphasize, coincidence is not causation. Venezuela lies along an active plate boundary where magnitude 6 events occur with predictable regularity. Any genuine space weather connection, if it exists at all, would likely be subtle, perhaps nudging the timing of quakes already primed to rupture, but not driving them outright. The most scientifically responsible conclusion is one of restraint. While electromagnetic or gravitational coupling cannot be completely ruled out, there is no convincing evidence that such effects play a significant role in seismic activity. For earthquake preparedness, space weather monitoring offers no practical advantage. Risk management must remain grounded in well-established seismology, plate boundary dynamics, historical catalogues, and probabilistic hazard models. Part 13. Novae and Climaton. Even more speculative question arises from September's twin stellar explosions. Could distant novae exert any influence on Earth's climate or geology? Here the scales involved quickly put things into perspective. A typical nova releases roughly as much energy as the Sun emits over 10,000 years, an extraordinary figure by human standards. Yet distance matters. Both V1935 Centauri and V7994 Sagittari are thousands of light years away. By the time their energy reaches Earth, it has diluted across such vast distances that the additional radiation amounts to little more than starlight. Over the course of their brightening and fading, the total energy Earth receives would be too small to warm even a single cup of coffee. Contrast this with supernovae. Unlike novae, true stellar explosions on this scale can affect planets tens of light years away. If a supernova occurred within about 50 light years of Earth, the flood of gamma rays and X-rays could disrupt atmospheric chemistry, potentially destroying portions of the ozone layer and exposing the biosphere to harmful ultraviolet radiation. Some researchers have suggested that past mass extinctions may align with evidence for nearby supernova events, though this remains speculative. The mechanisms involved are primarily atmospheric. High-energy photons can split nitrogen and oxygen molecules, producing compounds that break down ozone. Separately, cosmic rays from supernova shockwaves could, in theory, influence cloud formation by seeding condensation nuclei, possibly affecting climate on much longer timescales. Experimental support for this remains limited, however, and certainly far removed from the faint, distant novae of September 2025. Media coverage often blurs these distinctions. Reports suggesting star explosions may affect Earth's climate rarely clarify the difference between a nearby supernova, potentially consequential, and a faraway nova, which is visually spectacular but physically irrelevant to our planet. This blending of categories fuels dramatic narratives at the expense of accuracy, encouraging the public to connect events that in reality remain entirely separate. The clustering of earthquakes, solar storms, and novae in late 2025 provides rich ground for storytelling. Yet the physics of energy scales and distances makes any direct causal links between those novae and earthly processes impossible. What we are left with is not a chain of physical consequences, but rather a convergence of human perception, a reminder that meaning often arises less from mechanisms than from the stories we weave around them. The total energy that will ever reach Earth from both September novae across their entire observable lifetimes amounts to less than a single second of ordinary sunlight striking our planet's surface. Yet the scientific investigation of stellar explosions and their potential climate influence remains both valid and fascinating, provided that research stays anchored in plausible mechanisms operating over appropriate timescales. The galaxy produces supernovae at an average rate of 1 to 3 per century. Over millions of years, Earth inevitably encounters radiation from relatively nearby stellar blasts. Geological archives sometimes preserve signatures of these encounters. Isotopic evidence, such as traces of iron-60, a radioactive element forged almost exclusively in supernovae, has been discovered in deep-sea ferromanganese crusts and in Antarctic ice cores. These detections serve as direct markers that Earth has, at times, been bathed in enhanced cosmic ray flux, originating from stellar explosions. Such isotopic signatures are tantalizing, but they point to influences measured not in months or years, but across millions of years. Current evidence suggests Earth experienced elevated cosmic ray exposure about 2 to 3 million years ago, likely linked to supernova activity in nearby stellar associations. Whether that exposure altered climate, atmospheric chemistry, or even evolutionary trajectories remains an open question under active study. Some researchers have speculated about links between variations in cosmic ray flux and the onset of ice ages. The proposed mechanisms usually involve cosmic rays altering cloud nucleation processes, which in turn could influence global climate. Yet the evidence remains mixed, the models incomplete, and the causal chain unproven. For the September 2025 novae specifically, any climate influence is purely academic. Their effect on Earth's radiation budget is effectively zero. They will not alter atmospheric chemistry, disrupt ecological systems, or register in climate records. Their role is to illuminate the night sky and to expand our understanding of stellar physics, not to impact terrestrial weather or geology. This contrast offers a crucial lesson: perspective. The cosmos routinely produces events of staggering scale, novae, supernovae, galactic collisions, black hole mergers, that unleash unimaginable energies. But distance and dilution mean that, in most cases, Earth feels no measurable consequence. Our climate system responds overwhelmingly to solar variability, volcanic eruptions, greenhouse gas concentrations, ocean circulation, and other planetary processes operating across years to millennia. Exotic astronomical influences may occasionally imprint themselves over geologic epochs, but in day-to-day or even century-scale climate they remain negligible. Still, the human impulse to connect distant cosmic outbursts with earthly events is deeply ingrained. Psychologically, pattern-seeking behavior once aided survival by detecting meaningful correlations in a chaotic world. Today, that same instinct can tempt us to perceive causation in coincidental clusters of unrelated phenomena. The clustering of earthquakes, solar storms, and novae in September 2025 offers a perfect canvas for such projections. As we leave behind speculative links between novae and climate, our attention turns to another extraordinary phenomenon, one that provides a far more direct opportunity to explore how the solar system interacts with the wider galaxy. Among the events of late 2025, perhaps none is as scientifically promising as the arrival of a third interstellar visitor. Part 14. Interstellar Visitors. As solar probes, 3i Atlas represents more than an astronomical curiosity drifting through interstellar space. It may be the most sensitive natural probe humanity has ever encountered for studying how the Sun interacts with material formed around other stars, whereas Oumuamua raced out of view too quickly for sustained study, and Borisov remained distant throughout its passage. This third interstellar object enters under far more favorable conditions. Its trajectory threads directly through the ecliptic plane, the region of highest solar wind density and most intense space weather activity, just as the Sun approaches the peak of solar cycle 25, when coronal mass ejections, CMEs, erupt with maximum frequency and magnetic complexity. Comets, by their nature, act as natural plasma instruments. Their ion tails visibly trace the otherwise invisible magnetic field lines embedded in the solar wind. Sudden bends, disconnections, or brightness shifts provide real-time diagnostics of solar wind speed, density, and direction, as well as of CME impacts. For decades, heliophysicists have used solar system comets as remote sensors. With 3i Atlas, that principle extends to material with an entirely different chemical and isotopic history. Matter condensed around another star, in another neighborhood of the galaxy, perhaps billions of years ago. The upcoming Mars flyby on October 3, 2025, makes the opportunity even more remarkable. Unlike Earth-based observatories limited by viewing geometry, spacecraft around Mars, including ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter, will observe the interstellar visitor from a vantage point just 0.19 astronomical units away, about 28 million kilometers. Mars Reconnaissance Orbiter's high-rise camera, though built for imaging planetary surfaces, will achieve effective resolutions near 30 kilometers per pixel when pointed toward the object, sufficient to distinguish broad coma structures from a compact core. ExoMars's spectrometers may add another layer of insight, detecting emissions of molecules such as CN, CO, or CO2 released as sunlight warms interstellar ices. Such detections would be the first direct chemical fingerprints of volatiles formed around another star, liberated under the heat and magnetism of our Sun. Meanwhile, ground-based observatories and amateur astronomers worldwide are coordinating through the International Astronomical Union's Minor Planets Center to maintain continuous coverage. Amateurs, with their ability to provide high-frequency observations, will fill in temporal gaps that professional observatories cannot cover, capturing short-term changes potentially linked to specific CMEs. There is precedent for dramatic interactions. In 2007, ESA's Stereo spacecraft recorded Comet Encke's ion tail being completely severed by a CME, a spectacular demonstration of magnetic reconnection in action. If 3i Atlas undergoes a similar tail disconnection, the event would mark the first time scientists have observed the Sun's magnetic field directly reshaping matter imported from another stellar system. The stakes extend beyond space weather physics. Interstellar objects carry isotopic signatures of their birth environments. Solar heating and spectroscopic analysis may reveal clues to stellar nucleosynthesis, supernova enrichment, and the chemical evolution of distant regions of the Milky Way, observing how billions of years of cosmic ray exposure have altered 3i Atlas compared with fresh solar system comets could also reveal much about the interplay between interstellar radiation and icy bodies. In addition, the encounter doubles as a planetary defense test case. Although 3i Atlas poses no risk to Earth, the tracking, orbit determination, and chemical characterization techniques refined here will be vital should a hazardous interstellar object ever approach more closely. The implications touch even on astrobiology. If 3i Atlas carries organic compounds or prebiotic molecules, their detection would provide evidence that the raw ingredients for life may be widespread across the galaxy, not confined to the solar nebula that formed Earth. With perihelion on October 29th and closest approach to Earth on December 19th, the interstellar visitor offers an extended window of study stretching well into 2026. Coordinated observations during these milestones backed by modern space, weather monitoring and global collaboration, promise to unlock discoveries that were simply out of reach during previous interstellar encounters. Part 15. Looking forward. October and beyond circle the dates: October 3rd, 20th, 21st, 29th, and December 19th. Each represents a key moment in what may become one of the most extraordinary observational seasons in modern astronomy. On October 3rd, 3I Atlas sweeps past Mars, providing the first opportunity in human history to study an interstellar object at close range, with spacecraft not originally designed for such encounters, yet uniquely positioned to take advantage of them. Simultaneous Mars-based and Earth-based observations will yield parallax data that sharpen our estimates of the object's size, structure, and activity. October 20th to 21st brings a different spectacle: the close approach of comet C2025-R2 SWAN at roughly 0.26 AU, coinciding with the new moon and the peak of the Orionid meteor shower. Under dark skies, observers may witness an interstellar visitor, a bright solar system comet, and multiple meteors per hour, all against the backdrop of heightened solar activity. It is an astronomer's perfect storm of cosmic theatre. Finally, October 29th marks 3I Atlas's perihelion, when solar heating reaches its maximum and the comet's activity may peak. Each of these milestones offers opportunities for data collection, for public wonder, and for reflection on how events in our own solar neighborhood connect to the broader galaxy. The convergence of interstellar exploration, solar cycle dynamics, and coordinated global observation makes the months ahead a turning point in how humanity studies and understands its place among the stars. This close approach to the Sun will expose the interstellar traveler to heat intense enough to unlock volatile compounds, sealed within its icy nucleus for millions of years, during its passage through the interstellar void. Observations around perihelion could determine whether 3I Atlas behaves like familiar comets or reveals traits unique to its alien origin. The warming may spark sudden increases in brightness, the growth of spectacular tails, or even fragmentation events, any of which could distinguish interstellar visitors from solar system comets born under different conditions. Although its perihelion keeps it farther from the Sun than Earth's orbit, the geometry ensures excellent visibility for ground-based telescopes throughout late 2025. Global observing networks are already in place, prepared to monitor brightness fluctuations, spectroscopic changes, and tail dynamics as the visitor endures its moment of maximum solar heating. On December 19th, the object reaches its closest approach to Earth about 1.8 astronomical units, or roughly 270 million kilometers. For comparison, this places it nearer to us than Mars at its farthest distance, ensuring favorable viewing conditions for both professional observatories and dedicated amateurs. Unlike Oumuamua, which sped out of sight before detailed study was possible, 3I Atlas will remain observable well into early 2026, giving scientists an extended opportunity to watch its evolution under shifting solar conditions. Still, expectations must remain realistic. Interstellar visitors and comets are famously unpredictable. Some exceed every forecast with dazzling displays, others fade into obscurity. The most probable outcomes here are modest, gradual brightening or fading, subtle spectroscopic signatures, and evolving coma or tail features, scientific gold, but not necessarily naked-eye wonders. The true breakthroughs are likely to come from chemical analyses, isotopic studies, and plasma interactions, rather than breathtaking photographs splashed across the media. Meanwhile, Earth itself remains immersed in peak solar activity. As solar cycle 25 maintains its maximum, the Russell-McFerran effect around the equinox amplifies the likelihood of intense geomagnetic storms. These disturbances can generate vivid auroras, disrupt communications, and test satellite resilience. The NOAA Space Weather Prediction Center continues its vigilant monitoring, while spacecraft across the heliosphere track the Sun's coronal mass, ejections, and their potential encounters with both Earth's magnetosphere and the path of 3I Atlas. For aurora chasers and space weather enthusiasts, the coming months may deliver some of the most dramatic skies in years. On the ground, seismic monitoring continues across Venezuela after the twin earthquakes of late September. While aftershock activity remains under observation, seismologists emphasize a sobering truth. Earthquakes follow the rules of tectonic stress, not solar storms or cosmic alignments. Preparedness, building resilience, and sound engineering remain the most effective defenses, not speculative links to astronomical phenomena. In parallel, nova monitoring presses forward. Both V1935 Centauri and V7994 Sagittari continue their slow fade, with professionals and amateurs worldwide contributing photometric data that helps unravel the physics of these stellar explosions. Months or even years of observation will chart how ejecta expand, cool, and sometimes form dust that dims their light. Satellites like Fermi and Swift provide high-energy insights, capturing gamma rays and X-rays from particle acceleration in shockwaves. Here too, careful data collection takes precedence over sensational speculation. Taken together, October and the months beyond will be defined not only by what unfolds in the sky, but also by how humanity responds to it. The temptation to link earthquakes, solar storms, nova eruptions, and interstellar travelers into one grand narrative is strong, but science demands restraint. Each phenomenon follows its own laws, yet the coincidence of timing offers a powerful reminder of how dynamic and unpredictable the universe can appear when cycles briefly overlap. The call to action is clear. Observe, participate, and contribute responsibly. NASA, ESA, the USGS, NOAA's SWPC, and the International Astronomical Union provide trustworthy updates, while citizen scientists can play an active role by photographing comets, tracking auroras, logging nova brightness, or reporting seismic activity. These contributions enrich the scientific record while deepening personal connection to the cosmos. In the end, the deeper question lingers. Does the clustering of so many phenomena in late 2025 point to hidden connections? Or is it simply a striking case of coincidence? Perhaps the answer is less important than the perspective gained. For the first time in history, humanity possesses the instruments, coordination, and knowledge to monitor such a convergence across disciplines. From distant novas to local earthquakes, from solar storms to interstellar wanderers. Conclusion. What emerges from this remarkable season is not proof of cosmic causation, but a profound reminder of human progress. We are the first generation able to see the universe in such detail, to recognize overlapping cycles that would have passed unnoticed in earlier centuries. Whether coincidence or connection, the September-December 2025 cluster reveals a universe alive with change. And within that universe, humanity now stands not as passive witness, but as active chronicler, measuring, questioning, and learning. The ultimate lesson may be that the cosmos will always surprise us, but the greatest story is our own capacity to recognize those surprises, separate fact from illusion, and find meaning not in imagined links, but in the shared pursuit of understanding.